we have a truck driving down the road, and this truck collides with the fly. So we're going to be talking about collisions for this unit. From Newton's third law, the thing that we know is the fly and the truck have equal and opposite forces. So if we look here, I know that the force from fly 1 is equal and opposite to the force by the truck. So the net force of their collision is going to be 0. So if we added the two forces, it would be 0. So we're going to first use Newton's second law to rewrite this. What is Newton's second law? F equals ma. So what we're going to do, we're going to have the opposite of the mass of the fly times the acceleration of the fly equals the mass of the truck times the acceleration of the truck. Okay, so we're just rewriting this. We know acceleration is just the change in velocity over time. So we're going to rewrite acceleration. So we have the opposite of the mass of the fly is the change in velocity of the fly over the change in time, which equals the mass of the truck times the change in velocity of the truck over the time. Now we're talking about the time of their collision. So what do we know about these two times? They have to be equal, all right, because it's the same two objects in the system. So those are equal. So therefore, I know that the mass of the fly times the change in velocity of the fly is going to equal the mass of the truck times the change in velocity of the truck. But from last week, what is mass times the change in velocity? Momentum. So now I have the momentum of the fly, and if you want, you can make that the change in momentum. So the change in momentum, because we have change in velocity, so change in momentum of the fly is equal and opposite to the change in momentum of the truck. Okay, so therefore the truck and the fly have equal and opposite change in momentums. Okay. So in a collision, we're kind of looking, we have two very different objects because it's a collision though. If they're coming together and they're pressing on each other, we have Newton's third law, and then going through and combining everything, we can see that even though the objects are so different, when we talk about their mass, we talk about their velocity, their momentums are going to be the same, okay, or their change in momentums are going to be the same. So let's go a step further here. Let's look at the relationship with the velocity. So what we have the same thing here. So I'm just moving this up here now. And I'm going to take the opposite of the mass of the fly, and I'm going to put v prime of the fly minus v of the fly. So we already have a subscript f for fly. So I'm going to use prime for final, and then no symbol for initial. So this is the final velocity minus the initial velocity. So that's the notation I'm using to represent the change in velocity here. And that's going to equal mass of the truck, and I'm going to do the same thing for the truck. The change in velocity of the truck is just v prime of the truck minus the initial velocity of the truck. And then go ahead and distribute the masses on both sides, and be careful for your symbols on the left-hand side here. So here I have my final velocity, initial velocity. Final velocity, initial velocity. What I'm going to do next is I'm going to add this initial truck mass velocity, so the momentum here, I'm going to add it to the other side. I'm going to add this to the other side. So what I end up with is the mass of the fly, initial velocity of the fly, plus mass of the truck, initial velocity of the truck, equals the mass of the truck, final velocity of the truck, plus, because I'm going to add this, so plus the mass of the fly and the final velocity of the fly. And what do I know about mass times velocity? What is that equal to? All right, so this is the momentum of the fly before the collision plus the momentum of the truck before the collision. So this is the total momentum before the collision. So total momentum before the collision. And then over here, I have the momentum of the truck, the final momentum of the truck, plus the final momentum of the fly. So this is the total momentum after the collision. And notice just by simple use of algebra and moving things around, what we're seeing is the total momentum before is equal to the total momentum after. So if you have a conserved system, so that means there's no non-conservative forces. So that's your friction, your sound, like anything that's transferring outside of your system. If it's conserved, the momentum before is always going to equal the momentum after. And this is kind of the big idea of conservation of momentum and where we're going to be headed in terms of the understanding that we're looking for. So we have the conservation of momentum here. Assuming there's no external forces acting on the system of objects, the total momentum of all the objects in the system remains unchanged. So we know that net force then is going to be 0. It's useful for analyzing collisions and explosions because of Newton's third law, because we know we have equal and opposite forces. A collision is an event in which two or more objects approach and interact strongly for a brief period of time, but an explosion results when an object is broken up into two or more fragments. So we're always going to use this equation, P before equals P after, and we have 3 types of interactions, and so let's take a look at those. We have explosions and collisions. An explosion, you have a shared mass, so you have objects that are either together, like multiple objects together, or even just one object, right, and it explodes. And what happens is, this is my initial, so I have one object, so it's the sum of their masses, and they have velocity or don't have it, but it's a shared velocity because they're connected in some manner. Afterward, they're separate, so then we would split up their momentums into 2 equations because they would have their own momentum. But ultimately, even though each object or combination of objects, they each have their own momentum when all is said and done. So this is just a matter of saying if this happens before, this happens after, and we don't lose any energy or we have no forces that we're losing energy from, then these two are going to be equal. So even though we have 3 different values here, the before is going to equal the after. So an inelastic collision, that is when you have separate objects, they come together and then they stick. Okay, so we have 2 separate objects for this particular example. You can have multiple. You can have 3, 4, 5. It doesn't matter. But if they come together, they stick. Then we add the sum of their masses, and then we take a look at their velocities. So here, technically, with an inelastic collision, right, the kinetic energy is not conserved. Okay, and the reason why is because if they deform, all right, then there's going to be a transfer of energy. So that deformation transfers energy. Now I'm specifically talking about kinetic energy versus our gravitational potential and elastic potential. I'm specifically referring to this because these are objects in motion. So the energy we're generally looking at is a kinetic energy that we're doing that. That doesn't mean it can't have those other ones. It would be the total energy. It just happens if it's in motion in the examples that we're looking at. It's just the total energy happens to be kinetic. All right, but it's the total energy here not being conserved. For elastic collisions, we have objects. They hit each other, and then they bounce away, and we're saying they're doing that without much deformation. Now, with that said, so here our energy, our kinetic energy, would be conserved because we have no deformation.